next speaker.
Okay, thank
Or
you.
speakers.
Thanks again, Mr. Chairman. So our next topic that we are going to be presenting is Advanced Seismic Safety Studies, and that will be presented by Dr. Norm Abramson, our Chief Seismologist. Norm has well over 29 years of experience in this area, and he has a PhD in seismology from UC Berkeley. He's also an adjunct professor at both UC Berkeley, UC Davis, and looking forward to his presentation.
Actually, we're supposed to start with Stu Nishenko. We just saw him walking outside. I think they're going to go. There he is. So Stu will give you the introductory part on the source characterization, and then I'll follow up with what that means in terms of ground motion. So it'll make a little more sense to have him run through the source part first.
That's a good order to do it in.
All right.
Here comes Stu right now. There he is, right behind you. Guess who's on, Stu? You were introduced 10 seconds before you walked in.
Good afternoon, good evening.
Thank you.
How are you?
We're doing well.
Good. So I guess we just jump right into it. So I guess this evening, Norm Abramson and I are going to brief you on the results of the Central Coastal California Seismic Imaging Project Report. And I have about 15-20 minutes. We can go through this, and as you know, this is a project that PG&E conducted in response to recommendations from the California Energy Commission, who wrote the AB 1632 report in 2008. So my name is Stuart Nishenko, and I served as the technical manager for the field operations portion of this project. So the idea behind, I think, the recommendations was a recognition that in the 20 years since the original LTSB had been conducted, there have been significant advances in geophysics, data acquisition, data processing. We can hit the next slide. This shows some of the areas where we've had advances in instrumentation, data processing, the advent of differential GPS navigation, and certainly geographic information systems, things we didn't have in the 1980s. So all these together have created what I call, next slide, this revolution in resolution in the earth sciences. We're just able to see things in unprecedented detail, more detail than we could in the 1980s. Next slide. So using that increase in resolution, we attempted to identify about 10 specific parameters that were key to seismic hazard assessment and try to reduce the range of values that we had to deal with to do our hazard assessment. So this slide shows on the y-axis the 10 values that we had identified and vetted with the help of the PUC's independent peer review panel. So things such as the slip rate of the Hosgri fault, slip rate of the shoreline, whether there was a possibility for the shoreline and Hosgri fault to link, what was the total length of the shoreline fault zone. So parameters like this, and it's presented in this slide in terms of a tornado diagram, where we're basically looking at the ratio of hazard values at a fixed point, which has a return time of about 10 to the minus 4 at 2G. So this is spectral acceleration at 5 hertz. And we're looking at the variation in hazard around that fixed point for the range of parameters that we had for each one of those items on the y-axis. So you can see between 2011, when we identified these parameters after we finished the original shoreline fault zone report, and today in 2014, some of those parameters we've been able to significantly reduce the range in values.
Could you give a little background on what these parameters are at the lay level that you are? I think I can imagine what slip rate is, but dip and step over,
So,
I'm not sure I can.
Absolutely. So what we're interested in to do hazard assessment, you have to know something about the frequency at which earthquakes are occurring, the geometry of the faults at which the earthquakes are occurring on. Is it a vertical strike slip fault? Is it a dipping reverse fault? And all these have implications in terms of how close the fault plane is to the plant, the sense of motion, and factors like that. So when we did the 2011 report, we had, again, information from the original LTSP. We wanted to improve our understanding and just determination of what those parameters were. For instance, the Los Osos fault. We had values that went from a low of about 35, 40 degrees up to about 75 degrees. So as wide range of dip values has a big implication on what the ground motions you can see at the surface are. You'll see later on with the examples and the work that we've managed to constrain the geometry of the Los Osos fault to actually be much steeper dipping than we had originally thought.
It looks like it's within the uncertainty range, but it's on the lower end
Right.
of the uncertainty range.
So we managed to narrow the uncertainty in a lot of these parameters.
Right.
which
And
then
in
moving
general,
forward-
it looks like the original estimates had conservatism in the sense that I assume that parameters to the left are better than parameters to the right, or am again, I just am trying to be able to interpret the
Yeah, I think it all depends on your definition of conservatism. For instance, the Hosby slip rate, we were looking at a range of rates that went from 0.5 millimeter a year to 6 millimeters a year.
Mm-hmm.
So now we've been able to reduce it down to 1 to 3 with a higher level of confidence. So again, reducing that range then reduces our uncertainties. Okay. So these were the parameters that we're interested in addressing with the field work that we conducted as part of the seismic imaging program. Yes, sir.
I just want to clarify the exchange between you and Per. I just want to clarify the exchange between you and Per. The word conservative doesn't apply here, I think. You're trying to make the best estimate you can and capture the uncertainties as best you can, as I understand it and as I've read the report.
Yeah.
So the fact that the Hosby slip rate is now thought to be constrained to between 1 and 3 rather than 0.5 all the way to 6 means that when you do the analysis, you have more confidence in the ultimate hazard that you end up with at the site. But whether it's higher or lower is just the chips will fall where they may, right?
This is true
In other
for
words-
that example.
Yeah,
yeah.
for that example. But now let's just take the Los Osos dip rate. If it's going like this compared to going like this, it makes a higher hazard, but that's not, or lower, but that's not your point. Your point is merely to understand what it is so that you can put it in the hazard calculation. Is that
Yes,
right?
that's right.
So I don't think, unless I got you wrong, I don't think that the analysis you did before or the analysis you're doing now has conservatism in it, does it?
Well, for those two examples you presented, I think you're absolutely right. However, some of the other examples where we have were the shoreline and Hosby fault linking together. Based on the geometry of those faults, we think that it's highly unlikely that rupture would propagate from one fault onto the other.
But you can't exclude it.
We can't exclude it, so for the purposes of conservatism, we looked at the consequences
I understand.
of
That's
that
a
jumping too.
difference.
So,
A good counterexample. But in terms of the numerics and so on, I just thinking these parameters are what they are, and they go into your calculation as they come out.
right, I'm just an empirical guy, and I'm just trying to get the best values that we can for those.
Let me
parameters.
express just a small amount of skepticism. In general, when one performs uncertainty analyses like this and generates probability distributions, you deal with your uncertainties by introducing conservative bias into the analysis, and that's quite standard. And so it's not at all uncommon that as one improves your understanding and therefore can put in more better information, that you will see this convergence towards the less hazardous rather than more hazardous into the spectrum that you had before, which is apparently what's going on here. Now, maybe it was just But
We hope so.
no, I understand. And furthermore, if these blue lines were at the other end and it ended up over there, then you'd have, that would be interesting too. Or if they were someplace substantially different from where the yellow lines are.
Remember, these are ratios about a mean value. So either you're less than the mean or greater than the mean. But in terms of how then that translates to hazard, because we're looking at the specific parameters. So, for instance, 6 centimeters and 6 millimeters a year, you're going to have a faster moving fault than you would at 5 millimeters a year. So here we're shifted towards the low end of the range rather than the high end of the range. But the point of this is that we went into the project with a set of parameters that we wanted to gather more information about, and we had vetted the investigation of these parameters with the PUC's IPRP, their independent peer review panel. So it was coordination and collaboration between us and the Public Utility Commission.
But looking at this, the main improvements then have been in a better understanding of the geometry of the faults as well as their slip rates.
Right.
Yeah. Which is good.
I mean, some of these, because some of these, the major faults are underwater, so it has been difficult up until now to get that basic information. Okay?
Yeah, go on.
All right, continue. So, next slide, please. So this is just a diagram of the low-energy seismic survey work that we conducted offshore. The top figure just shows it as sort of a schematic sense. 2 types of survey activities that we conducted. To the right, we have what we call multi-beam echo sounding, which we use to do high-resolution bathymetric mapping of the seafloor itself. And then to the left is a schematic of the ray paths for what we call low-energy seismic reflection surveys. So here you're producing sound and listening to the echoes as it reverberates off of layers beneath the seafloor. The photo on the bottom shows one of the vessels that we use to do these low-energy surveys, and it carries behind it what we call a P-cable array, which is an array of 14 50-meter-long hydrophone streamers that represents really the state-of-the-art in the oil and gas industry and how you do these sorts of low-energy surveys. So we were one of the first to actually bring this outside the oil and gas industry to use it for non-exploration kind of purposes. The thing to be aware of as we go through some of the examples is, given the geometry, what we call the acquisition geometry of that array, we were able to conduct bins or construct bins which have dimensions of about 2 meters vertical, about 3 1/8 meter horizontally. So that really defines the minimum spatial resolution that we have for looking at geologic features on the seafloor. Next slide. This is an example, this is sort of great before and after example of the kind of technology that we had in the 1980s on the left as part of the original LTSP, where you basically constructed bathymetric maps using soundings and did contour intervals. The figure on the right shows that same area offshore Diablo Canyon with the multi-beam echo sounding imagery that we collected in 2009, 2010. So you can see very clearly between the 2 red arrows the surface trace of the feature that was named the shoreline fault zone, existing 600 meters offshore of the plant. But again, a much greater clarity and resolution than we did with the old data. So this is part of that revolution and resolution that I referred to before.
Just out of curiosity, the surface data to the right, to the upper right, above, that wasn't. You didn't use a boat to get that.
No, that's LiDAR, right?
That's LiDAR. Okay.
That's LiDAR data.
All right.
But again, the same idea that we were able to just use all that new technology.
Understand. Okay.
Okay. Next slide. So the next 2 slides are just going to review quickly the survey activities that we did conduct. So number 1 is pre-AB 1632, if you will, is work that we did as part of our long-term seismic program, doing the multi-beam echo sounding and some potential field mapping offshore of the plant. So this occurred right after the recognition of the shoreline fault existing offshore the plant. That happened in late 2008, so this is work that we started doing in 2009. In late 2010, we started to conduct low-energy seismic surveys both to the north and south of Diablo Canyon. And if I had you guys know where Diablo Canyon is, right?
But one quick question.
Right there.
In, I guess, 2000, the discovery of the shoreline, was that off of the bathymetric images, or was that from what
Seismicity.
From seismicity in that area, microseismic activity aligning along that trace? Then,
Yes.
right? Okay.
So to kind of reel back a little bit.
And then when you come in and look at this, you say, oh, yes, that does look like there's been some faulting.
Well, the coincidence of the epicenters with that bathymetric feature, and then also with a number of marine magnetic anomalies in that central section,
It all came together.
to indicate that there was a tectonic feature there.
I
So
mean,
what we
How old is this fault? I mean, how long has it taken for things to move and create this feature on the surface?
we'll get into that a little later in the presentation.
Sounds good.
Okay. But part of the initial investigation was to just get a better understanding about what the geometry was. How long is the fault? Where does it hook up or intersect with the Hosbury Fault to the north of Point Bouchon? What's the nature of that intersection? And also, how far south does it extend into San Luis Obispo Bay? So these were two areas of investigation that we wanted to look at, as well as number 3, which was to start doing onshore seismic reflection work in the Irish Hills and the Los Osos Valley. This is an area that had not been as thoroughly investigated, say, as the offshore had been during the LTSP. So the charge was to look at, faulting in and around the area, so we took advantage of that opportunity. The next slide shows the continuation of activity in 2012, where having gotten a lot more experience using low-energy techniques, we started to focus on specific sites where we could get estimates of the fault slip rates. So again, looking at geomorphic features in the shallow seafloor, and looking at offsets of those features to help us understand how fast the shoreline fault was slipping, how fast the Hosbury Fault was slipping, were two of the primary objectives shown in 1 and 2, as well as in item number 3, we continued doing onshore seismic work on the western side of the Irish Hills and in the area around Diablo Canyon. And Norm is going to talk a little bit later about high-resolution tomography that we're able to do underneath the plant site itself so that we could further characterize the site conditions at Diablo. Next slide. This just kind of shows a schematic diagram of what you can do with digital data. This is a block in San Luis Obispo Bay, and if you click the next slide, you can strip off the water layer, expose the seafloor for investigation. Next slide. Identify a particular horizon at depth, and then be able to strip off the sediment above that horizon. Next slide, please. To look at the structure at depth. In this case, this is the bedrock surface underneath the more recent sediments. So what we're able to do with low energy, this 3-dimensional low energy seismic program now is analogous to going to your doctor's office and getting a CT scan instead of a typical X-ray. So the CT scan, allows us to look at this in different angles and orientations and interrogate it a lot more effectively than we could with just vertical seismic profiles, the kind that we're able to do in the 1980s. So the next slide shows that basement surface again in a little more detail.
What's the depth of this surface, roughly?
So the surface is about 50 meters below the seafloor.
Oh, okay.
And there's about 25, 30 meters of sediment on top of that.
How old is it?
So this is for the most part, Cretaceous sandstone.
My dad can do that, but I can't.
70 million years
60,
old.
70 million, okay.
Okay. And then there are other...
I don't do that stuff, but he does.
more recent sediments and the more recent Neogene
Cretaceous.
sediments on top of it.
That sounds really Cretaceous.
But this is the hard stuff. This
So
is
there's
what we call
dinosaur
the-
footprints, or the resolution is not so good to see those? Sorry.
I just told them that the dinosaurs are in the Cretaceous.
Excuse me?
This is the time of the dinosaurs when this was on the surface.
Well, yeah, and not only was this on the surface, but at the time, this particular image, well, what we're looking at here is the result of numerous low sea level stands.
Sure.
So 20,000 years ago, sea level was about 100 meters lower than it
Because
is
of
today.
glaciation.
It's exposed.
And San Luis Obispo Creek, which is right outside the door here, actually drained out across the continental shelf.
Yep, the
To
same
the
up
edge.
around the Bay Area.
And so that's what you see is that gully that running through the center of the image there
That was a valley.
that was a valley that was eroded numerous times in the past during multiple low sea level stands associated with glaciation. The most recent one was 20,000 years. There's another one about 125, another one about 240. But reoccupation of these features created that gully. And what we want to do then is look where the faults cross those geomorphic features to see the
Because you can
offset
spot them more easily here.
right on the walls.
And this is things that have happened since these sediments were deposited. So this is faulting in the last 60 million years, or was some of it precede this?
Faulting in the last 100,000, let's say.
Hundreds of thousands.
Hundreds of thousands,
Hundreds
okay.
of thousands, yes. So what we do is we use the overlying sediments as part of the
Oh,
stratigraphy.
as you go up, you can get dating on when.
Right, we
when
try to develop a relative dating scheme and then look at the amount of offset as a function of distance.
That's great. Well, at least you don't have to worry about glaciers ever happening again. No, it's not a joke, unfortunately. But that's long enough in the future that we don't have to worry about it right today anyhow,
No,
so,
no.
okay.
Sometimes, though, that would certainly make things a lot easier to look at under the seafloor. So, but what we're able to see is, again, using high-resolution seismic data. In the past, surveys have been done in this area where the spacing between boat tracks was 800 meters, or half a mile. Here, the spacing between survey lines is in the order of 12 to 15 meters. So it's high-resolution data collection, and that with post-processing and signal processing, we're able to bring out a lot of the more subtle features in the seafloor topography or the basement topography than you could see or hope to see with just
How
simple
big are these
vertical
data
lines.
sets?
Excuse me?
How big are these data sets? They must be ginormous.
Yeah, terabytes.
Terabyte, yeah. That would be impossible to have done that 5 or 6 years ago.
Well, and this is typical of the kind of technology that exists in the oil and gas industry. That we're
This is
able-
fracking, actually, because, sorry. Microseismic, okay, anyhow.
Yeah, so, again, we're
We're
swords into plowshares,
benefiting from
okay?
fracking, yet again, right here.
No. Swords into plowshares. So what
Okay.
you can see on the figure is, again, the very sharp lineations associated with the shoreline fault zone, the oceano fault zone. I wish I had a laser pointer. I could go into this in a lot more detail. Does somebody have a laser?
Okay. No, it's okay.
Just because we're so excited about this.
Yeah, no,
this
it's
is a really big step forward.
It's great.
So, sit in the top right. All right. So here is the shoreline fault zone as it cuts across the section. The Oceano fault zone, another major fault zone that had been recognized, but now have much clearer mapping, and a third one called the Los Berros. And what you see is all three of these fault zones are converging towards the top northwestern portion of the section. There's a rock here called Sousa Rock, which is a navigation hazard offshore that is in the vicinity, again, where all these faults are intersecting with one another. And what we can see in looking at the marine sediments on top of this surface is that the rate of motion of the shoreline fault zone, again, is on the order of hundreds of millimeter a year, and the rate of horizontal motion to vertical motion is about 10 to 1. In contrast, the Oceano fault zone we see over here is predominantly a vertical fault. So it's a vertical high-angle reverse fault with a rate of about 1/10 of a millimeter a year and very little evidence for horizontal motion. It's mostly vertical. as is the Los Berros Fault. So the Los Berros, the Oceano are all part of what we call the southwest boundary zone, which together contribute towards the uplift of the area.
I was reading this great big report you guys sent around, and I was trying to understand, I was trying to understand the shorelines, the sense. It's almost all horizontal and there's a little bit of vertical,
Right.
but I had the impression that it was very hard for you to resolve how much vertical that was. Did I misunderstand that?
It depends on the age. Okay, because of this 3-meter cube issue that we have, we can only resolve features that have offsets greater than 3 or maybe 6 meters. So looking at the most recent motions, it's very hard for us to resolve. However, looking at older strata, where now the cumulative offset has accumulated beyond 3 to 6 meters, you can clearly see it. But with some of the horizontal horizons, we actually see evidence for vertical offset of older horizons. Okay, within our resolution limit. And again, the ratio of vertical to horizontal is about 1 in 10.
When you're talking about older, that's a few 100,000 years old.
Yeah, yeah. And you'll see an example here next.
Okay, thank you.
One of those features. So what I'm going to do right now in the next slide is just kind of show a paleo shoreline that exists right here in the southeastern part of this section, where we've been able to get a fairly robust slip rate. But in addition to that shoreline, of course, there are other stream channels that we've been looking at to come up with a number of examples of slip rate as a function of time. So next slide shows that paleo shoreline. And again, based on stratigraphy, the top panel is uninterpreted, the lower panel is our interpretation, and you can see that there's a jog right there in that shoreline surface. We've been able to date the age of that shoreline as somewhere between 155 and 185,000 years, again, based on stratigraphy. And so there's about approximately 10 meters of right lateral offset of that shoreline. So it gives us, that's where we get the rate of 0.06 of a millimeter per year over the last 160,000 years.
6/100ths of a millimeter.
Right, or 60 microns.
60. Okay, 60. Okay, thank you. I heard it the other way, and I was impressed by that. Was a very large rate, but that 4 orders of magnitude makes a difference.
Right, because they're averaging over a long period.
But the uncertainty in that is what? What would you say? Factor of 2?
I think the major uncertainty is the age of the feature.
Yeah,
which again, though, we have our preferred rate, which is our preferred age, which is somewhere around 160, 165 million. But again, that's based on relative stratigraphy. It's not based on an absolute age date. So there's where we recognize in the report.
So you could be off by
if you were
30, 50,000 years or something. You could be off by a third or something.
It's possible, yeah.
But is there any way that you could, if you were to core in that area, where there'd be dating, would that be worthwhile to try to get a better date?
That
would probably be expensive.
That is one of the possibilities to further constrain.
Okay. All right.
Thanks, Norm.
To get absolute dates. So all these are based on a relative time scale. It's internally consistent.
But you can also trace these stratified features to areas where you might be able to get access to them and date them better, or is it?
Most of the wells are to the south and farther offshore. We try to do that and then just stratigraphically trace it across.
Okay. All right.
So we were able to do a similar kind of analysis for the Hosgreave Fault, and probably one of the best sites that we identified is right offshore Point Sal, where again we identified a series of submarine channels, most likely related to drainage of the Santa Maria River. And this picture here shows 3 channels that have been subsequently offset by the Hosgreave Fault in probably the last, I want to say, 300 million years. I'm sorry, 300,000 years.
300,000. Okay.
300,000 years.
So maybe I've missed it then?
So our estimate of the rate of offset of the channel to the west relative to the channel to the east here is on the order of 600 to 650 meters. So that's a well-defined parameter. And our age of that channel, as I said before, is about 342,000 years, equivalent to isotope stage 10. So dividing that offset by the age gives us a slip rate of about 1.8, 1.9 millimeters a year, which is consistent with other estimates of slip that have been determined farther north.
That's a lot larger than the shoreline.
Yes, it's about a factor
lot larger.
of 10 or more larger. So in a relative sense, the Hosgri is still the primary source.
But previously, you couldn't exclude something as big as 5 or 6
on the Hosgri.
per year on the Hosgri, and now you've brought that down to thinking that it's not likely to be higher than about 3, is what I...
Yes, I think that's fair to say.
Right.
So we've halved the values at some uncertainty level. But still, even having that value, we're looking at a rate that's, let's say, 2 millimeters a year versus a rate on the shoreline, which may be on the order of 1/10 of a millimeter a year.
You know, on the Hayward Fault, which I live 300-400 feet from, it just there's structures on the ground which have been offset by 10 inches just in the last 70, 80 years. It's you can measure it almost real time, I think.
So it gives you a context. It provides a context. So now it's sort of a relative context between the activity of the controlling source versus the activity of the secondary sources.
Maybe I need to move.
No, you don't want to move.
It's a beautiful climate.
We live in the East Bay. Norm lives in the East Bay. You live in the East Bay?
No, I live in the West. I live in the peninsula.
Okay.
Got it worse.
In between the two, yeah. So again, another example of the kind of work that we're able to do with this high resolution, shallow seismic imaging and low energy seismic imaging. Of course,
has this been applied elsewhere for this kind of purpose of characterizing earthquake faults and earthquake hazard?
this is one of the first applications. Again, most of this is being used in the oil and gas industry for exploration. And this was, I think, in Sam Blakesley's mind when he started this whole process, is to take some of that technology and use it for other purposes.
It's actually pretty phenomenal.
Yeah, I agree. Thank you.
Now, may I ask you, there's no dispute here, just listening to you, that now within 3 years, you have more precision in measuring some of the key parameters. As a matter of fact, you just indicated the Hosgri move maybe 10 times faster, the slip rate, maybe 10 times faster than the shoreline. Or more, right? Yeah. May I ask you, what interpretation can we walk away from that measurement?
Okay, a lot of that interpretation work is going to be addressed in the SHAC study that we're in the process of completing as part of our response to the 54F letter. And because that is taking a probabilistic approach to looking at seismic hazard, for the purposes of writing this report, we wanted to compare it to what we did in the 2011 report, and we took a deterministic analysis as opposed to a probabilistic. So while we have created this data set, we don't necessarily take advantage of it in this report, but will in our report that's going to come out next March.
Right, so you are just providing the facts and let the interpretation come later.
And the uncertainties.
Right, okay.
So the next slide. One of the other projects, if you will, that we've investigated, remember when we got the recommendation from the Energy Commission to do 3D seismic, they were silent on what kind of 3D seismic to do, because there's high energy and there's low energy, and we made the decision that we would investigate both paths and start doing the low energy first, because our contractors had permits to do low energy seismic surveying, because the source is less than 2 kilojoules, and it was allowed by the State Lands Commission, while we explored the possibility of doing high energy work with air guns. And so we laid out a plan went through the permitting process, were granted a geophysical permit by the State Lands Commission, and then subsequently denied by the California Coastal Commission, I think primarily on the grounds of environmental concerns, that using air guns in shallow coastal waters would be environmentally detrimental. Nevertheless, we were interested in the question of what high energy could tell us about deeper structure in the crust, and specifically the whole issue about the geometry of the Hosbury Fault. During the LTSP, there's a lot of controversy about whether the Hosbury was a vertical strike-slip fault or whether it was dipping off to the east, a low-angle thrust fault, or maybe even a listric kind of fault.
Now, may I ask you, what drives the controversy? Was it difficulty of measuring things, or is it difficulty of interpreting things? What drives the controversy?
There were, I think, basically there were two camps at the time. In terms of geologists interpreting data from areas that they're familiar with. So there was a group that wanted to have most of the major faults along the California borderland being low-angle listric faults, such as they saw in the transverse ranges. And the other group, which using some of the geophysics that have been collected in the Santa Maria Basin, saying that it was a high-angle strike-slip fault.
Right.
But in the 1980s, of course, we did not have the advantage of a long period over which to collect data and information. So now here in 2014, we've basically doubled the amount of time that we've done seismic monitoring in the region, as well as increased the kinds of studies that were able to be accomplished. Not only seismic, but also other potential field studies like gravity, magnetics, and observing and recording more earthquakes.
So has that controversy been resolved to your satisfaction?
In our report, we think it has.
Okay.
And the point of this slide is just a comparison with the depth of penetration into the crust that these different techniques can provide you. So previously, we were talking about low-energy seismic surveys, and the depth that those surveys penetrate in the crust is illustrated schematically by that little red bar that's up on the top of the diagram. So typically, you can get 200, 300 meters penetration in the crust. With air guns, high-energy surveys, what we've seen in the studies that were done in the 1980s, you can get penetration down to maybe 5 or 6 kilometers and get clear imaging. Okay, you can also get penetration much deeper, but the imaging is not as clear. However, even at 5 or 6 kilometers, you are above the seismogenic zone. Most of the earthquakes that are occurring along the Hosbury, as you see in that slide, are typically happening at depths greater than 3 or 4 kilometers, down to about 15, 16 kilometers. So what we've done is we looked at the geometry of the fault zone that's illuminated by the hypocenters themselves, as well as inversions of crustal structure that you can get from gravity and magnetic data, which typically give you greater penetration, as shown in this slide here. So the combination of potential field data and seismicity is consistent with a high-angle vertical Hosbury fault. And it's also consistent with the imagery that you get at shallower depths as well. So the point of Chapter 6 of the report is that we really don't see strong evidence for a reverse fault or listric faults that were previously hypothesized.
Now, in reading that, I kept asking myself whether you were willing to exclude that, the shallow reverse, or whether you just thought maybe the SHAC PSHA is going to assign probabilities to that. I mean, that's its role. Right. It looks like a much lower probability that that's the correct interpretation.
A dipping fault.
Yeah.
Yes. Mm-hmm. And in fact, in one of the slides or the figures in the report, it kind of shows a sensitivity where if you change the dip of the Hosbury, the variation it had on the magnetic field values kind of helped to constrain the dip as vertical instead of being more shallow.
Yeah, and it has a lot of sensitivity to the actual hazard at the site.
Yes, it does.
Now, are you saying things are happening at the depth of 15 kilometers or so, and with multiple technological advances, you now had confidence that things at that depth can be either measured or interpreted or, or somehow interpolated, extrapolated? Is that what you are saying?
Yes. Okay, now part of this is, we've had, instead of 20 years of seismic activity that we've recorded, now we have 40 years of seismic activity. So more advances in our ability to more accurately locate earthquakes with respect to one another. And this is, again, one of the things that led to the identification of the shoreline fault zone, shows that the lineation of the seismicity of the hypocenters actually define a vertical plane. So this is something that the USGS has come out and said, and is also what we have said as well. So you can look at the seismicity itself as being an indicator of the geometry of the fault, and also then look at patterns of magnetic anomalies or gravity anomalies, again with the assumptions about composition, because you have to make some assumptions about rock properties to model those anomalies. But again, all three are consistent with this interpretation of a vertical fault.
I assume, and maybe there would be some discussion, how does one go about estimating potential for return frequency or actual risk of earthquakes on, say, an annual basis on a specific fault? If you look at, again, the Hayward, that I live on top of, the return frequency is so high, I think it's roughly every 140 years or so, that I think you can fairly readily characterize the risk, and it's, we're overdue is what I've been told. But on something that is moving at 60 microns a year, then is there an approach to estimate the annual risk of or probability of a fault or earthquake occurring on the fault, or?
That's going to be the second part of the presentation.
Oh, please.
So we'll hand it off to Norm.
I'll answer that.
Yeah, he'll hand that. Okay. But the point being, though, even though we were denied the high energy permit, we nevertheless did the due diligence to look at. Oh, I'm sorry. The point being that even though we were denied the high energy permit, we did the due diligence to look at other geologic and geophysical data to help us answer the question. And the answer is that we have a vertical Hosgry fault. So, next slide. What I'd like to do is spend a couple minutes talking about the land seismic, if permitting. I know we're going over schedule here, but I hope you permit.
This is important.
So this is a picture of about 4 or 5 vibra-sized buggies that we ran in and around the Irish Hills in 2011 and 2012. So this is the on-land equivalent of high-energy seismic reflection profiling. And the strategy that we wanted to adopt for doing all this work was take a top-to-bottom approach. So we integrated surface geologic mapping with shallow high-resolution seismic profiling. You saw the less examples in the marine. The onshore example is what we call accelerated weight drops. And then for deeper imaging, we use these vibra-sized trucks. Each one weighs about 65,000 pounds. And to get us penetration again down to 5, 6, 8 kilometers. And you'll see some examples in the upcoming slides. So the next slide shows a geologic map of the area in and around the Irish Hills. And Diablo Canyon is shown as the circle there in the lower part of the diagram. Overall, we conducted survey activities on about 110 miles worth of access roads in and around the plant and the Irish Hills. Now, this is a lot more difficult to do than when you're out on the water, because the Irish Hills is a very steep topography. You're limited to where the roads are. You just can't drive out over the water like you can with a boat. So, and landowner issues provided, if you will, sort of patchy coverage in what we can do. So the feasibility of doing true 3D profiling like you see in the marine work was somewhat limited. We managed to do a lot of tomography as opposed to amplitude 3D, and you'll see some of the, well, it's shown in the report. Next slide. So this is a fence diagram that just sort of summarizes the major elements of our interpretation of the geology and geologic structure of the Irish Hills. So the key thing here about the Irish Hills is that it is an asymmetric basin that was formed in the Neogene about 22 million years ago in what we call a trans-tensional regime. So here you have active spreading and opening of these basins. And then about 3 to 4 million years ago, coincident with change in plate motion in the Gulf of California, it went from trans-tensional to transpressional, and that basin closed again. So there's very clear evidence in looking at some of these faults where you can see reversal of motion, where at one period it's acting as a normal fault, and then as the basin is closing, those normal faults reactivated as high-angle reverse, and you see development of little anticlines and folding on that feature. So the Edna Fault, which is mapped on the surface in the center of the Irish Hills, seems to be the major structural boundary of this basin on the northeastern side. And there are a number of hidden, or what we call blind faults, also associated with the Edna Fault system that we're able to map at depth. It's a very steep fault on the order of 60 to 80 degrees depth. The Los Osos Fault further to the east is also a steeper fault. The dips that we get vary along strike of the fault and range anywhere from 55 degrees up to about 80 degrees. The Los Osos Fault at the surface doesn't really exhibit a lot of evidence for strike slip faulting, so we're characterizing it as mostly reverse or reverse oblique kind of sense of motion. But it doesn't seem to be as well developed as we previously thought. In fact, to the north, as you get closer and closer to Morro Bay, it actually dives and goes blind and seems to be a fault propagation fold rather than an actual fault surface. So it's more developmental. On the western side of this fence diagram, of course, we have the shoreline fault, which is been demonstrated to be a steep vertical fault based on seismicity and other geophysical modeling. And then we have the San Luis Bay Fault, which cuts across the Avila Beach Gate here, right down the road, and kind of obliquely cuts across the Irish Hills and then eventually joins up with the shoreline fault further to the north. This fence diagram only shows, if you will, the top few kilometers. We believe, though, at depth that all of these faults converge or coalesce into a single root zone associated with the Edna Fault zone itself. So it's like a flower structure, originating from where the Edna Fault is and then branching out.
And all the evidence you see here is consistent with that hypothesis of that switchover 4 or 5 million years ago between the extensional and then it suddenly changed.
Right, closing, yeah.
Hmm? And all this is all consistent with that?
Yeah, so it's consistent. It provides, if you will, a tectonic model or a framework with which we can understand then the particulars
Do you have
of the geometry.
anything that puzzles you or that contradicts that model? Or that's in
Again, this is a hard place to work, because this is not the classic layer cake geology.
Oh, no, it's the opposite. The whole of California is like that. You
Yeah,
know that better
and this
than I
is
do.
the Franciscan, so it's very broken up, and you'll see in the next two slides, actually, what we've had to deal with. So what I want to do is show you some slides and kind of compare this geologic cross-section with a proponent model that we have been addressing as part of the IPRP process at
Right.
AB 1632. So could I have the next slide? So
Hamilton.
the top is a cross-section that was proposed by Dr. Douglas Hamilton in 2012 as part of his testimony to the Public Utility Commission, where he made a number of predictions about the geometry of certain faults in the area. And the two that I want to focus on right now is the Los Osos Fault to the left-hand side of the slide. I'm sorry. Thank you. And the inferred offshore thrust, which Dr. Hamilton has proposed, is an essential feature of the geology of the hills in order to explain the uplift of the Irish Hills. So the top figure is a geologic cross-section drawn primarily from surface geology and then extended downward. So what we've been able to do now with the data collection we've done as part of the seismic imaging process is provide images of the crust at depth. And to the right is a cross-section through the Los Osos Fault that demonstrates a steeper dip than the 45-degree dip that was originally proposed. And that steep dip continues along strike of the whole feature. To the right is a cross-section through the San Luis Bay fault zone. And you can kind of see the fault zone itself there delineated by the two parallel vertical yellow lines. But what we wanted to show you is that the projected zone where Dr. Hamilton's inferred offshore thrust is proposed to exist shows no evidence of cross-cutting that vertical fault zone. So the white area there on the profile on the lower left is the range where his proposed fault is. And in looking at the data that we have, we really don't see any evidence for vertical faults being offset by subhorizontal faulting, and rather feel that the geology in that particular area is best represented just by a steeply dipping San Luis Bay fault. Now, this is not to say that we disagree with the whole observation that, in fact, the Irish Hills are uplifting, but we need to look at and are considering other models to explain the uplift of the Irish Hills. One model, of course, is the role of the Los Osos and the southwest boundary zone. Again, it's a series of reverse faults dipping towards one another, producing the uplift. And then we're also looking at perhaps other offshore faults like the Hosgri itself that may be what we call the uplift rate boundary that contribute to the observed uplift of the Irish Hills. But this is just sort of a comparison of what we're able to see with the reflection profiling versus older proponent models that have been proposed for the area. So it allows us to look at this with greater clarity. Next slide. The other proponent model or proponent issue that we dealt with in this report concerns the observation of the Diablo Cove Fault. So this is a feature that was uncovered during the excavation of the plant during the 1960s. It's shown here in the figure between the two red arrows. So we do not dispute the fact that there's a fault there. The issue is just how large of a fault, how significant of a feature is it? Is it seismogenic? Does it represent a seismic hazard or a surface rupture threat to the plant? The next slide shows...
The fault is right next to the microphone.
Yeah, so it actually goes underneath the corner of the turbine building.
Right where it's shown.
Right, okay, it's right there, right?
Yeah.
Okay.
But the question is it seismogenic or not?
Right.
Right, is it seismogenic or not? So the next slide shows the attitude of the fault in some of the excavations that were conducted at the plant site during the initial construction, and the photograph on the right shows two pictures of the fault itself. So the key things here are when you look at the fault itself, there's not a lot of displacement across that feature. When the fault was originally mapped by Professor Johns in the 1960s, the observation was made that on top of the bedrock surface there is a quaternary alluvial terrace deposit that's dated about 125,000 years. The fault does not disrupt that terrace deposit. So that was taken as evidence for lack of activity within the last 125,000 years. And then on top of that, looking at mapping of the fault trace on the surface, it's discontinuous and and the surface traces that are mapped do not follow the same trend, but they go off in different directions. So it's a discontinuous feature. It hasn't been active in the last 125,000 years. We don't see evidence for significant or any offset at depth based on the high-resolution seismic profiling that we did in and around the plant site. So what we would describe this is a secondary faulting feature, something like a bending moment fault that gets created when you're bending and folding rocks, rather than a through-going seismogenic structure. So for that reason, we...
Is there any way to actually estimate the age of that fault? Or is it's older than 100 and some odd thousand years, but
Yes,
beyond that, there's...
that's right.
Okay.
I mean, we think that it's probably formed, again, during this period of basin contraction 2 or 3 million years ago when everything changed from opening to closing. But to find we haven't found other markers to actually give it
This was, I should say, some sort of a discontinuity that developed then, but it's not the same as a fault.
Right, yeah. So, again, the classic mechanical
I understand the
example,
distinction,
bending
right.
a beam, we have extension and
And your interpretation is if it was a fault, you've got 120,000 years of affirmative evidence there wasn't anything there. There wasn't any motion.
that's correct.
Right.
And
And then you don't see any displacement at depth either.
that's what I was
Right, so there's the two pieces of evidence, okay.
And the idea was that the trace of this fault would extend offshore and potentially connect to the shoreline fault zone, and we do not see any
didn't see that.
convincing evidence
Right.
that there's offshore connection
Okay.
with what's mapped on land. So all 3 lines of evidence have led us to disregard this as a seismic threat to the plant itself. Next slide. The third element of the seismic imaging project was to install an array of ocean bottom seismometers offshore of Point Buchan so that we could monitor the area in and around the intersection of the Hosgui and shoreline faults in more detail. So the picture on the right shows one of the permanent OBS installations. It's a 1-ton concrete cap which contains in it a 3-component accelerometer and a 3-component broadband seismometer. The cap is installed to basically prevent the instruments from getting injured or damaged during fishing, trawling activities or other things on the seafloor, as well as to provide some protection against storm waves and that kind of activity.
There's people out there trawling and dragging nets on the ground.
Outside the 3-mile limit, yes.
That seems unenvironmental.
That's
true.
It's in federal waters, so it's a completely different jurisdiction than what we can do in state waters.
Okay.
But it's a hazard if you have instrumentation on the seafloor that you have to be
It's a
aware
hazard
of.
to everything on the seafloor.
Yes. Well. The other key element of this deployment is that all 4 OBS units are connected via cable, so we have real-time monitoring capability. Most OBSs, or not most, but a lot of OBS units are, independent units that sit on the seafloor, and then you have to recall them to download the data. This, because we have a projected project life of 10 years, wired them up so that we could interrogate them in real time when earthquakes happen. So we are installed that array last summer. So the final slide, this kind of is a summary table of many of the parameters that we've been discussing here this evening. And just quickly, I do want to go over some of the highlights of the work that we've done, the results that we've achieved before I hand it over to Norm. So starting from the top, the Hosgui slip rate, we originally had a range that went from 0.5 millimeter to 6 millimeters with a preferred rate at 2 1/4. Based on the work that we've done, we think the preferred rate is around 1.8, 1.6 millimeters a year. So we basically halved that range. The shoreline slip rate, in 2011, when we did the original report, we had estimated a slip rate on the order of about 1/3 of a millimeter a year. We now have evidence that it's considerably less here, 0.06 of a millimeter, maybe 1/10 of a The issue about could the Hosgri fault rupture north of San Simeon during the LTSP, the boundary between the Hosgri and the San Simeon fault was considered to be a hard boundary, so rupture could not propagate through. For this report, we have relaxed that assumption and allowed rupture to occur through that area. So the step over between the Hosgri and San Simeon is not considered to be a permanent barrier to rupture. So you can get larger magnitude earthquakes on the Hosgri fault.
Yeah, but it's further away, and so it doesn't make as much difference.
Right, and that's part of what...
Compared to if it was closer.
Yeah.
Yeah.
But nevertheless, it is one of the key tenets of the original LTSP. Could there be a linked Hosgri shoreline fault rupture? In the 2011 report, we did not consider that as a possibility given to the unfavorable angle intersection between the two faults based on dynamic modeling. We still feel that way, but given the global data set that shows that 2/3 of the time when faults are within 3 or 4 kilometers of another, there is a tendency to jump from one fault over to the other. We have analyzed that scenario. So while we don't have convincing evidence that those two faults have ever ruptured simultaneously together, because we don't have age dating of individual events on both of those faults, for the purposes of our analysis and for the purposes of investigating the consequences of that link, we've linked them together, and Norm will talk about that a little bit later. And then finally, at the bottom of the slide, in the 2011 report, we had mapped the shoreline fault as having a total length of about 23 kilometers. Ooh. Based on the continued mapping that we've done in San Luis Obispo Bay, we've basically doubled the length of that fault, primarily due to extending it south through San Luis Obispo Bay. So the total length now from where it intersects the Hosgri off of Point Buchan to its southern terminus near Guadalupe and Point Sal is now in the order of 45 kilometers. So we've basically doubled the length of the fault, and because we've doubled it, it's become slightly more capable. So the maximum magnitude length relationship would go from a 6.5 to maybe a 6.7.
So what you're saying is a longer fault is a more capable one?
Yes.
Okay.
Yeah.
I don't want to use that word.
So
The word capable is the wrong word.
Well,
capable of larger magnitude events.
I just paraphrased what he said.
No, but that's the wrong word to use. The longer fault is longer, and therefore you could imagine developing more energy on it than if it were shorter.
Yeah.
I was trying to, the word capable has a legal meaning in NRC that really isn't technically useful, I think. That's why I was objecting to it.
Oh, but I like that word.
But I don't.
It means exactly what I want to hear.
This is an academic dispute. Given the hour, I do recommend that we now move forward absent addition. And let's do both presentations, then we can have discussion and entertain public comment, because the presentations are so closely coupled together. So Norm, if you could continue.
All right, thank you.
What's your last name, Norm?
I'm like Cher. Everyone knows me as just Norm, and that's the in the ground motion world. Norm Abrahamson. I'm the chief seismologist at PG&E Geosciences. So let me start by answering a few of your questions that will help bring all this stuff together, I think. So the first part is, in doing seismic hazard analysis, there are two approaches. One we call a deterministic approach, where we postulate an earthquake has occurred, and then we estimate what the range of ground motions could be if that happened. And it doesn't keep track of how often it occurs. Okay? The second approach is a probabilistic approach, where now we're going to say, all I want to be concerned with is, how do I get large ground motions at my site from any of the possible faults, and I'm going to add all their contributions together and keep track of the chance or the rates that those happen. Okay, so now some of this, these studies were prioritized based on their impact on the probabilistic results. So the NRC is moving to using probabilistic results for our risk assessment. We need probabilistic results, so that's the kind of information we were after. They were not prioritized to optimize the deterministic results. Okay, so the sensitivity diagram Stu showed you in the beginning is impacts on probability. Okay, in terms of chances of large ground motions happening. The ground motions he talked about is near the design basis of the plant, just so that you have a level of what we're getting at. The second question you had asked is, well, how do you get the rates of occurrence? You know, how often do these earthquakes happen? Because this is now sort of all tied together with this. So the way we do this is we use a common currency of seismic moment. Okay, and if you take the area of a fault and the amount of slip that's on it times the rigidity of the crust, we're going to talk about the work done by the fault as it moves. Okay, so we can get an energy release from that. So think area. So the area of the fault is important. That's all it is, right? Okay, so straightforward. So that's how much is released in an earthquake. But now, how do we build it up?
But of course, some of it is gradual. There is slip, and then there is
correct
abrupt releases.
So when we calculate these and calibrate our models of how do we relate area and so forth, how do we calibrate those to magnitude scale? That's all done with empirical data, so that we have it from the seismogenic part of the rupture, not the aseismic slip part. So the Hayward fault that's creeping, that's not releasing seismic energy that we're worried about. Okay. So then the second part is, well, now how do you figure out how much energy is available? So we use the same basic concept, but we use the area of the fault and the rigidity, but instead of the deformation, the slip, we're going to use the slip rate. See, since you are academics, I can tell you it's a time derivative, right, of slip, the slip rate. So now I'm going to so the key parameter there then is area of the fault and the slip rate. Mm-hmm. So the higher the slip rate, if I double the slip rate and everything else is the same, I double the rate of earthquakes. Okay, so if I was comparing the Hayward fault and the Hosbury fault, and I looked at them and said they're both 100 kilometers long, then I would say 9 millimeters a year on the Hayward fault versus 2 millimeters a year on the Hosbury fault. I would have earthquakes about, if I could divide 9 by 2, 4.5 times less often on the Hosbury as on the Hayward. Mm-hmm. And you thought about the 140 years, multiply that by 4.5, and now we're into the 700, 800 year recurrence intervals.
But easily, that's well within the range that you have to have within your design basis.
Absolutely.
In terms of return frequency and nuclear facility related risk.
Mm-hmm.
Okay.
But I'm just trying to
But then the shoreline actually might almost screen out if it's an order of magnitude slower slip rate and less area.
You don't screen it out, you just include it.
It may end up below 10 to the 4.
We do not screen out.
Okay.
Because we're going to sum.
You treat it through
We
probability.
don't
We're
screen
going to
anything
sum them
out.
all together, and so if I
Nothing gets
have
screened out.
10 small things, they add up to a number that matters. So we don't screen out the contribution. We put it all in there. Some of them become insignificant, okay, so that they don't matter.
They screen themselves out.
Correct.
Okay.
All right? But we don't go and say, I'm throwing this one out.
But, and I know the answer to this question, but I'm going to ask it so you can explain it. Imagine that I have evidence that a fault has, and it's a vertical and it strikes slip and it's absolutely vertical, and it has moved a meter in 10,000 years. All right? Now, there's a big difference between that's 1/10 of a millimeter per year, and it's just doing that gradually every year. And a house built on top of that, you wouldn't notice too much, versus once.
Mm-hmm.
And for a paleo evidence that might be a long, long time ago, how can you differentiate between those, or how do you deal with it in your probabilistic analysis?
So if we do not have evidence of creep, that we can see there's active creep going on, then we assume it's all seismogenic. So
Yes.
it's all released in episodic.
And so you assume the episodic unless, so that is in a sense a conservative assumption. You don't know what else to do.
But that's the standard of practice in this business.
You don't know what else to do.
Correct.
And the evidence that it is really a gradual creep is
Very few faults creep.
I said unusual.
Yeah.
Right?
The Bay Area is
Yeah, I mean,
And
I
it's
understood that
really
before, but I was
an
trying to explore
unusual
that,
place
so-
around the world. You do not see creeping faults in general around the world. So
Thank goodness on the Hayward, though, because it's delayed.
we'll talk about that another time.
Hopefully I
This is
can
good.
retire first and move someplace safe, like
So-
Kansas.
Okay, but to put this all into perspective, when we started out on the shoreline fault in their studies, we had no direct evidence of the slip rate.
Yeah, nothing.
We had seismicity that defined it. We saw from the gravity and the magnetic data that were consistent with a vertical fault. The mechanisms on there, so when we look at how the little earthquakes are slipping, they're slipping primarily horizontally in strike slip, so we think it's a strike slip fault. But the only way that we got at a slip rate was to say, let me look at the gross geomorphology. What does it look like? And how does that compare to other faults we've seen around the world? So we said it's between sort of 0 and 1 millimeter a year, just based on that gross kind of an assessment. So a very large uncertainty in that value. Then what's done here now, what Stu showed you, is we are able to get an actual measurement of the slip rate, looking at those deformations. So we've gone from just looking at analogs around the world to try to get the slip rate to actually having some data to get the slip rate. So that's a huge step forward. Previously, in the 2011 report, with the range of slip rates we assumed, and an average of about a third of a millimeter a year that Stu mentioned, the shoreline fault contributed 20% to the hazard at a 10 to the minus 4 level. So that's not negligible.
Right.
Okay, that matters. With the new rates that we're looking at, which are about a fifth of that, we're going to see the shoreline fault contributing about 4% to the hazard. So now with that kind of a contribution, it's not really worth the effort to go out and say, let me try to refine that to a 50% improvement in the slip rate, for example. So he said, should you be going coring? If I'm going to do coring, I want to do it on something that matters more than that. So the Hosgri is still my big player in terms of activity rates. That's the kind of place that you would focus on. So
now,
we want to.
Dr. Abrahamson, you now are saying the Hosgri is about 4%?
No, the shoreline fault.
Oh, the shoreline, okay.
For the hazard.
With our now constraints on the slip rate, we see that it's a much smaller contributor to the probabilistic hazard. Different in case when we go to deterministic. Those are completely separate because it's not going to worry about how often it's happening.
On the other hand, it's longer, so there's a little more, but you'll come to that, I guess.
Yeah, so the other part is there was some discussion earlier on, are we in this business, were numbers done intentionally conservative or not, and how was it done? The seismic hazard approach is to be mean-centered and capture the scientific uncertainty. We want to be able to bring along all of the credible scientific models that aren't rejected by observations and data. Okay? So there was no intent to be conservative, and you have to be really careful because this idea of how often earthquakes happen, right? We talked about I'm going to figure out rates of earthquakes, I'm going to balance the rate of release of seismic moment with the rate of accumulation. Sure. So with my slip rate and my area of the fault, I have an accumulation of energy build up every year. I've got this budget that's going to build up. I can release that in a lot of small earthquakes or in one big earthquake. Or if I make an even larger earthquake, it's going to happen less often. So we get to what is sometimes counterintuitive on the probabilistic risk type of analysis. If I make larger earthquakes and link faults up, I'm going to get lower hazard because the earthquake happens less often. On the deterministic side, when I link them up, I'm going to get a bigger magnitude, so I'll get a larger ground motion. So what is conservative for deterministic is unconservative for probabilistic, and so we don't want to go there. We go best science and track uncertainty. Mm-hmm. And these studies that Stu described to you were geared at reducing the uncertainty by collecting the data so we can start to chop off ranges of models or pieces of models that are now inconsistent with observations. We still have a big range that's there, but that's the nature of how the science moves forward.
Now, just to pursue one thing about that, the whole logic of the probabilistic approach is precisely to enable you to pull together these disparate, well, faults and sources in a way that produces a coherent measure of the hazard at the site. I mean, that's the whole logic, is to enable you to do that.
Yes, and that you don't want to just say, let me look at one earthquake and evaluate it. You want to look at all of them, because you can get strong ground motions from moderate earthquakes, and you can get them from big earthquakes.
And the logic of the probabilistic approach is a mechanism that enables you to do that combination in a logical
To bring
way.
them all together to give you, say,
Right.
an evaluation of what's going to happen, and how do you pick an appropriate level to work with. So,
But, of course, the actual fragility of structures and equipment is frequency dependent.
Sure, you have to capture that too.
And so you need to really understand what is the energy imparted
Absolutely.
at different
Yeah.
frequencies. And
Absolutely.
where does that come out of this kind of
so
analysis?
we don't do it at just one frequency. We've simplified it here to show you 5 hertz, which is sort of at the center of the range that's
Okay.
important. We cover the whole broad frequency range.
But how can you predict the frequency at which energy will be delivered? What is it in the? I understand now the concept on slip rate, area, work rate, frequency with empirical models. But how do you say something about frequency of occurrence? But how do you say something about the spectrum that comes when you get the earthquake?
So that's empirically derived. So we take earthquake recordings from around the world, from these, magnitude 7 earthquake, and we see what the frequency content is, and we look
But
at.
they can vary a lot, right?
And so we have large
So you
standard
get-
deviations. So
Okay.
we don't have a single value. We have a broad distribution, and that is all part of the probability. So it's when we do seismic hazard, it's a combination of the chance that the earthquake happens, the probability of that,
Okay.
times where are you in the distribution of the ground motions? Is it average? Is it 1 sigma, 2 sigma?
This goes to a conversation we had a long time ago standing on Hearst Avenue, but the idea that you could have a relatively small earthquake, but in fact, just because of the distribution of where the energy is imparted, you could deliver enough energy at a specific frequency to damage something that you wouldn't
Correct.
expect a
So
small earthquake to damage.
it's more likely to get strong shaking
Mm-hmm.
at Diablo Canyon from a very open, unusually energetic, moderate-sized earthquake than it is from a larger magnitude.
And now that's an interesting point, because
That's for
does
sure.
the probabilistic assessment, this is like small break versus large break in terms of initiating events for
Thermohydraulics.
Do you actually see in the probabilistic space that you're dominated more by the more frequent smaller earthquakes that have the wrong spectrum?
Yes, and we need to decide what is small. So small is in the magnitude, moderate 6 to
Oh, of
6.5.
They're not small, but
Not
they're,
magnitude 3s or
they're
something
not
like
small,
that.
but they're moderate.
They're moderate,
Yeah.
but
Uh-huh.
it's much more likely to get strong shaking from magnitude 6 to 6.5 than from a magnitude 7.5, for
Just
example.
because the frequency is so much lower, but you can get the wrong, you've got this uncertainty about spectrum.
Correct.
Right.
Then this is actually quite analogous to this is the argument for using probabilistic
Okay,
methods,
absolutely.
is that you're looking at what gives you the greatest risk, and it's the things that happen more often.
Wait, but all of that other information is in the distribution as well. So there is a contribution from those other earthquakes, and it's captured in the right weighting.
It's all there, but the
mean,
argument for the probabilistic approach
That was the whole
is you
logic.
can get strong shaking from a whole range of earthquake sizes. So even a moderate magnitude 6 can produce very large ground motions, or a magnitude 7 can produce very large ground motions. But if I have 10 times as many 6s as 7s, then I'm going to have more of those, so I can a higher chance of getting a really rare ground motion out of one of them.
Getting a spectrum that
Correct.
aligns with your plant's fragility.
Correct. So
Thank you.
That's great. Norm.
I am teaching hazard again at Berkeley next semester, so if you want to come and sit in on it, you
Norm,
can,
can I come?
I see you more
Can I
frequently
come?
there than.
Okay, so
You never mentioned Shaq. It's okay.
so now Stu talked about the new information, right? And I'll get back to the slides and try to keep this as brief as I can. So the earthquake scenarios define a magnitude, they define geometry. Geometry is really important, or dip is really important for us because of something called a hanging wall effect. When you're on the hanging wall of a thrust fault, you can get up to twice the ground motions in the high frequency content than you get on the other side of the fault. So that's a really important parameter for us to work on. That's actually one of the most sensitive parameters. So we need to know the magnitude, the geometry, is it vertical, is it dipping, and where is the earthquake. When we build ground motion models, you said, how do we get the frequency content? I don't have a whole bunch of magnitude 7s recorded here in the Central Coast region. So we take data from around the world, from analog tectonic regions, so same types of active faulting areas. And from that, we can then build up a global ground motion model. And it tells us how things scale with magnitude, how it scales with distance away. And then we get the strength of shaking at all different frequency contents for an average rock site condition. Okay, now this is an important point. When we trade space for time, because I don't have enough time to get a lot of recordings, so I go from space and I try different locations and say, let me collect those. But in doing so now I get a worldwide average model. And an issue that we'll be addressing is how does that apply to our site? Does it work at our site? And we'll show you, because we actually have recordings at our site, we're able to calibrate the worldwide models to the site conditions at Diablo Canyon and start to make a spectrum that more accurately represents what the shaking will be like there.
Now, how much data are we talking about? How many different earthquake sites here in your global model?
Oh, in the global model, we now are running about, I think the latest data sets have about 20,000 earthquake recordings. From big magnitudes and big earthquakes, it's probably in the, let's say over magnitude 6 within 20 kilometers, we're near 1,000 recordings. Mm-hmm. When this work was done initially in the 1960s or 70s, even when Newmark had data to work with, you were looking at a handful of recordings worldwide. And everything was extrapolated from further distances. So we have a huge increase, orders of magnitude increases in the amount of data available to build our average model. So things are much better constrained than they have been in the past.
You'd also mentioned that the strength of the earthquake, and I assume spectrum also depends in part where it initiates versus where you are. And my understanding, for example, on the Hayward is that depending on whether it initiates on the south end or the north end, the other end, which they've got deep sediments, so Sassoon Bay or San Jose, one of those two places is going to see extremely severe, actually really frightening ground motion, because it will have everything propagate toward it, and it will build up in front of the break.
So we call that directivity effects, and the way that that's treated right now in these ground motion models is it contributes to that breadth of the distribution. Okay. So it's part of our broad standard deviation. So one way you get those really large ground motions or rare ones is you have a rupture,
far away,
right?
And it propagates to you. Okay.
And when you calibrate this worldwide database to the local site conditions that you learned about from the few recordings we have nearby, that enables you to narrow that down, but not completely.
Absolutely. There's still broad uncertainties.
Right. I mean, it's way better, but
Correct.
it's...
Correct. Okay, the next one.
Thank you.
What was that word, that something effect?
Directivity.
Directivity, yeah.
So,
It's a heck of a difference.
This is a picture, just a zoom in of part of the geophysical survey that was done on land. And the red dots, again, are where the vibroseis trucks were shaking. And then the blue dots are where all the seismometers are. Okay? Oh. So think of each red dot to blue dot is a wave path. And this is why we're able to get an image of what's going on.
Those blue dots were deployed forever. You laid that's like several thousand.
This is what the oil industry does. So it's
There's a lot of them.
It's an amazing data set. So what Stu talked about is the key here. We now have data that no one has ever had in terms of trying to characterize
So
the site
fracking
condition.
really has been an
This is
amazing,
not fracking
just an
at
amazing
all.
technology.
This is seismic
Swords to
exploration.
plowshares.
This is exploration.
Exploration. So,
Exploration.
but you can see where the plant is. We can't get a lot of sensors there, but there was a red set of lines there on the coastline. You can see where the discharge channel is. And so we're shooting rays, if you think about how the waves are propagating, underneath the power plant. Okay, and so from that you can do tomography and invert for what the velocity structure is. The next one. So this is just one example that we're seeing of the 3D velocity model. The grids are 5 feet in the vertical direction and 20 feet in the horizontal direction. The red, the orange colors there are high velocities, okay, 1,500 to 1,800 meters per second, very hard rock. The green parts there are closer to about 1,000 meters per second. And the blue on the top is the lower velocities in the, say, 600 meters per second. Right.
What,
Okay.
does this geometry, is it consistent with your understanding of the geology?
Well, this area, if you ever see the coasts, the discharge cove, and you look back, you'll see that we don't have flat layered beds, but things have been bent up.
Okay.
So it's very complicated geometry. This area was previous subduction zone, and the accretionary wedge is scraped off. We have this building up there, so this whole thing is a jumbled piece of material. Correct. But deeper, it starts to get more consistent. If we go deeper, we're back to sort of a layered model that makes sense. But this is a picture that have never had this kind of image before to really understand it. Previously, we had 4 borings through this, okay, which is what you can see. You could get a very different answer depending on where your boring was. So now we understand the variability of what's going on underneath the power plant, and you'll have different structures will be sited on different material.
Where in this image is the plant?
It's that cut, so there's kind of a cut there, but is near the top edge of the towards the north, and so that big orange blob.
So it's it's
underneath
got green
the power
stuff.
block area.
It's got green stuff under it. Is that
the northern end.
do we have the pointer here?
Yeah.
That-
What we're going to see is that there's a...
The power block is in this area here, and this is the northern end. This is actually where we have one of our free field stations here. We have
And in general, you prefer to be on stuff that has high velocity because that means it's...
higher velocities lead to lower ground motions typically, okay? So the softer ones tend to amplify more. But we're going to now see the amplification will be different depending where you are in the site
But
region.
not to steal your thunder, but we're about to see that there are plots here for the power block and for the turbine building, and they're different, even though they're not very far apart.
Correct.
Okay.
And
Right.
you're going to see that right here.
Right. So we're back to this. This is not a flat layered model, and you're not going to capture it that way. Okay, the next one, please. So this is an example. The black lines are the 4 borings that we had previously that were made in the 70s. And that was all that we had to work with from the velocities. So they could be as low as, sort of average near 800 meters per second or up at, 1,700 meters per second. What was used previously was an average value for the power block, which is embedded down to elevation 52 feet there, of about 1,200 meters per second. And then we had uncertainty on that. But we treated those as the entire site was all either low or the entire site was high. What you see here, the red curve is the velocity underneath the power block. This is the, not one point, but this is averaged over the velocity profiles under the power block. So this would be sort of the average condition. And it is still around 1,200 meters per second, but you can see we have velocity reversals, things going back and forth. That's because of the complex way the geology is not flat layered. The turbine building is a lower velocity, so it's going to have more amplification than the power block will. So you'll get larger ground motions going to the turbine building for the same earthquake than you would have going to the power block. In general, the velocities get a little lower as you go towards the coast.
No, the turbine building and the power block, of course, are coupled together in important ways, such as electricity from your emergency diesel generators needs to get into the power block.
These
So
are both important structures for us.
But I assume they're designed for all of that for the differential motion. They're not going to shake the same way in an earthquake. They will have different motion because they're going to be excited in different ways, and they're
Correct.
also just structurally different, so they have different resonant frequencies. So
They don't move together, if
they
that's
do not
what you're
move together.
asking. Yes,
Yeah,
absolutely.
yeah. Believe it, yeah, the building I was describing at UC Berkeley for our civil engineering faculty, at least they were symmetric, but
So now we now have this very detailed view. Even if we simplify it to single velocity profiles, we're learning quite a bit more about what's happening. In addition, we have, not shown on here, but free field sites or sites outside the structure where we recorded earthquakes, and those are on the softer sites. One is at 750 meters per second, the other is at 560. So those have some of the soil conditions that we saw on the previous plot. The next one, please. So for our site response, the traditional way to do site response is to use the global data, estimate the motion on rock, and then propagate it up through your local site conditions. Okay. What we're able to do here, because we have recordings from past earthquakes, in particular recordings from the San Simeon and Parkfield earthquakes that we can use to adjust those global models. Now, there's a key thing that we found as our data sets global have grown. We have found empirically what has been known or advocated for quite a while from the theoretical people, and that is a global average is not right. The wave propagation through the crust is a systematic, repeatable behavior. If I had 10 earthquakes in the same area go into my site, they're going to go through the same crust and they're going to not be near the global average. They'll be representative of that crustal property. A site, the geotechnical engineers will tell you, each site has its own personality, its own way it's going to respond. It's not going to respond like the global average. Well, from our new data sets that we've got, we can now see the relative sizes of that and how much of this broad variability that we put into our global model is actually...
Can you treat the material because at the site you measure earthquakes from different sources, you had San Simeon and others. If you can treat it as being elastic, then you can.
Correct.
You can, I guess, deconvolve from that.
Oh, and then, of course, the little ones are elastic.
Correct. And so that's why we are going to be, so these are far enough away that they are still in the linear range.
Well, this is also why we're very interested to confirm that from the San Simeon earthquake that the structural response was consistent with models.
Correct.
Because as long as you're in elastic range, it doesn't matter how strong the earthquake is.
From those earthquakes, we're able to measure the elastic properties of the building. So you can see there the damping and the natural frequencies. And those were actually even previous when the Kalinga earthquake happened. That was recorded in 1980 and used to calibrate the structural model that was used in the LTSP. So to make sure the natural frequencies you're getting out of your model were consistent with what the observations are. So there is an empirical calibration of the structural models that we have here that
and now you're extending this essentially to calibrate your models for the soils
correct.
beneath
and not just the shallow, not just that shallow top 100 meters, but it's affected by the deeper parts. So we can be thinking about the top kilometer of material and how it's affecting the ground motion.
But this then gets you much greater confidence that you're correctly predicting the energy delivered at different frequencies,
correct.
Which is important for fragility. So that's a huge step forward.
The ISRS, the in-structure response spectra have now a much firmer basis.
Correct. So the key to this, before you can do that, we're going to use the data, but we need to take out, so one earthquake might be more energetic than another.
You've got to take out the earthquake.
So I have to take out the earthquake source, and I have to take out, it may have a distance attenuation with distance, so we have to take those things out. So the way we do that is we use recordings at other sites to remove the average effect of the source and the wave propagation with distance from that earthquake. Then what's left gives me the site term.
Is this, when you do
Right.
this type of modeling, are you doing it with time-dependent models, or is,
Not time dependent. I'm not sure what you mean
oh,
by that.
I'm starting to think about, some of the simulations that are being done now for earthquake response actually use a time-dependent finite element model
What does
for,
a time-dependent model mean?
as opposed to, it simulates over time.
Oh, you're talking about a time domain model.
Time
No.
domain, sorry, time domain, excuse me, yes, it's,
We do, so we use recordings. So I'm going to then compare the data from that particular earthquake, recorded as a function of distance and at similar distances to where Diablo Canyon is, but not using the Diablo Canyon site, and compare that to my global model.
Okay.
And if they're all falling off steeper than my global model, well, I need to correct for that so I don't map
Okay.
a path effect into my source, into my site term. So it was, when we looked at the actual recordings, I don't have all the details here, at Diablo Canyon, these two earthquakes look completely different, very different frequency contents and so forth, but after correcting for the path and the site, and the source, getting that out of there, we're then able to see the site response, and then they're very similar, which is giving us some confidence that we're getting the right answer here. So the bottom line is we see a resonance in the 2 to 3 hertz range at Diablo Canyon that is stronger than the average, and we see weaker amplification above 5 hertz compared to what an average site would be. Now, each site is going to be different. Some will amplify and some will attenuate more at different
And you also see a
frequencies.
difference between the power block and the turbine building in that.
We don't because
There's-
all that we're able to do here is to compare our free field recordings with the global model prediction of what a free field recording would be.
Oh, okay. And so,
But it's
so
not-
then you-
it's
then
not
you can't make
predicting the
that-
power block.
But you ought to be able to see that if you had more data.
If we had more sensors in.
We had
would.
more local data.
Correct. And more earthquakes and more, you need that, if you're going to have local earthquakes, you also need a dense array of earthquakes as well. So there's a third earthquake that was recorded, it's called the Deer Canyon event. It's nearby, it's only 5 kilometers away. The problem is we don't have similar recordings nearby to take out the
take out
source
the
and the
site,
path, so I
take out the
can't
effect.
see the site through that. Okay. The next one. So this is what those terms look like. So there's a lot on this plot. X-axis is frequency, so that's the frequency of the oscillator. The y-axis here is in natural log units, but it's the deviation from a global model after we've corrected that model for the site, or excuse me, the path and the source terms. So I've gotten the average earthquake effects out, and I've gotten the average distance attenuation out. This is
Right.
what's left. If I didn't have any information from new earthquakes, I would have said my site 0 would be the global model. If it's here, then I'm fitting the average model around the world. The orange lines are giving me what the range of these models would be if I had no information. So there's a big range of what could occur there. The data points here, the red is from Parkfield and the blue is from San Simeon, are showing me how this is my estimate of how this site behaves compared to an average site around the world. Negative means there's less amplification. Positive means there's greater amplification. So we can see a shape here that's systematic, saying I'm going to amplify more in this range, I'm going to amplify less in that range.
right, so basically you have higher content in the lower frequency range.
Correct.
And in the higher frequency range where mechanical equipment, for example, may be more fragile, you've got
We have lower
less.
contact than an average would be around the
Right,
world,
but,
right?
But, and the range of frequencies, I think, where structures tend to respond, maybe it's,
They're
you've
in
got
here,
more.
right?
No.
And so also, if you're here and the structures are in this range, then they could be started to influence by this extra amplification.
And are the fragilities, people putting this in? I
That's
assume-
what we're doing now. We're
Yeah,
developing
I mean,
new
that was-
fragility models for the shape that comes out
Right,
of this
right.
site-specific type of a spectrum. The dashed lines here are our uncertainty range because we're only working with 2 earthquakes. We have actually 3 recordings, but I only count them as 2 because one of the earthquakes is recorded in 2 places on the site, and I don't want to count that one twice.
But are these methods being used in any other types of civil infrastructure? Because you can record earthquakes. I mean, you can put seismometers in buildings, and so, buildings.
This is one of my missions in the next 10 years is to increase the number of seismometers because showing people that you can actually use the data. Previously, one of the big impediments to installing instruments near structures was that they'd say, well, that will be 1 in 10,000 data points. It's not going to change anything.
Yeah, but it's really...
But if you use it for your site, then it changes things completely.
Yeah, because the Kobe earthquake, 5,000 people died, right? And so this.
You should be able to tell which areas amplify more and which areas amplify less. So
and also you can assess how your structures are going to respond.
Sure. Better. That's correct.
Better, yeah.
So our dashed lines here are our uncertainty ranges, and they're big. Okay,
I'd love to have just even a couple of more.
So to really get, you mentioned you can use little earthquakes, and that's correct. And so the way to start to get more data here to fill in this or to add more recordings is to put instruments that have lower trigger thresholds, but we need to get them in a quiet enough spot so that the
people walking around.
Or the noise. Being near an industrial facility is not a quiet place to run seismometers, so that's part of the trade-off of still being close by but not being shaken by all of the things that are going on there. The other part is that we did have 9 earthquakes, little earthquakes, recorded by that network of seismometers put out for the geophysical survey. So they're magnitudes 0 to 1. I mean, little tiny earthquakes, but they're recorded beautifully on those things. So we are in a data overload situation now where we have thousands of recordings because we have so many sensors. But that's our next part is to try to evaluate that because that is now so densely recorded around the area that we can have a much better picture of what's going on. The next one. So the other part is the issue. So what do we start to do with this information? So don't pay too much attention to this yet. We'll get to this picture. The data that we've been collecting that Stu mentioned for the source characterization is going as input to the SHAC study. So I think one of you, Peter had mentioned, this is data, right? Here's the facts, and the other group is doing the evaluation of that, the full evaluation. But we still need to say, are there any immediate impacts? Does this suddenly tell me I have a problem, I got to do something about it now or not? And so the way that we've done that evaluation is in a deterministic analysis. And so we've gone back to saying, let's run this in the way a deterministic analysis is done. In a deterministic analysis, bigger magnitudes, which is part of what Stu was finding, that we're going to allow a longer shoreline fault. So it can release a bigger earthquake less often, but a bigger earthquake. Or linking the Hosgri up to the San Simeon fault makes a bigger earthquake. Okay, linking the potential for the shoreline fault to link to the Hosgri fault produces a bigger earthquake. So what does that mean for us? Well, the point of this slide is that we're not very sensitive to the magnitude of the earthquake when we're talking about the high frequency shaking levels. And the reason for that is what I'm going to try to explain to you here. So on the left-hand side is a fault map, okay, and here's Diablo Canyon. The orange line is the shoreline fault, the 25-kilometer fault from the 2011 study. Okay, this is actually mapping out a tectonic domain here, but this green line, or this on this side, that's the Hosgri fault. So it's 110 kilometers long in this section here about. So if I'm going to take this fault and I'm going to say now it hooks up and ruptures here, makes a bigger earthquake, or I make the Hosgri fault continue on to the San Simeon and go further up, I'd have a larger earthquake. I'm going to have more energy released. We know that. But the energy will be released will be spread out over the length of the fault.
Right.
So the amount that's added close to you is actually not very much.
Is this because I think this also contributed for the Great Japan, or it was didn't have as much high frequency. I think it was lower because it was the same thing. It was coming from actually 3 faults.
There you can have things distributed over 1,000 kilometers long. I mean, just huge lengths that those things can
And the
be
high
distributed
frequency
over.
just doesn't travel. So
right.
the high frequency comes from what's faulted locally, the low frequency from further away.
Right. So there's a limit really of about 25 kilometers that influences the high frequency ground motion. And as we get
And
beyond
so-
that, it doesn't change very
You're 100
much.
I mean, we've always known, if you're 100 kilometers away, that stuff just isn't going to get to you.
So what's the logic behind the 5 hertz as being a good representative frequency to present data for?
That's where the equipment is.
The main structural models are in 3 to 8 hertz, so it's in the center of that range.
Okay. It's in the center of your fragility,
Correct.
key areas of fragility in the plant.
And the fragilities are keyed to this parameter.
Got it. Okay.
Okay? So if you look then how the ground motion models work. So this is the latest ground motion models that were developed last year, called NGA West 2, but these are the current models that are used. This is magnitude 5 up to magnitude 8. The red line shows what happens as the magnitude increases if you're 1 kilometer away. So think about the shoreline fault, for example. So if I go from 5 to 5.5 to 6, this is a log scale, so my ground motion is going up maybe here by over a factor of 2. But once I start to hit this 25 kilometer range, which is around a magnitude 6.5, then these curves start to bend over. There's very little increase in the high frequency ground motion close to the fault as I add more and more total energy to the earthquake because it's spread out over a large distance. So you can see here as I go from 6.5 to 6.7 or 7, I'm changing the ground motion by less than 10%.
But then this points towards the stronger earthquakes, or the ones that would involve a longer length. They will generate stronger ground motion at low frequencies. Is there anything that's really vulnerable at low frequencies? Basically, do you break all your underground piping? Do you slosh water out of pools? What are the vulnerabilities at the lower frequencies?
So those are
Fragilities.
evaluated. The lowest frequency that is considered in our current approaches is down to half of a hertz or 2 seconds.
Okay.
So cranes are things that are sensitive to that. Sloshing occurs, and sloshing will happen. There's no doubt about that. There's sloshing during the San Simeon earthquake. So sloshing of the spent fuel pool water will occur. But most of the safety-related systems and equipment tend to be stiffer. So equipment is stiffer and so
nuclear
forth.
structures too. So.
Right. But all of the full range is included. Okay. And in our new models, we're going all the way out to 0.1 hertz or to 10 seconds just to be complete.
Going down all the way down to 10 seconds just because you can?
Just because we can, the NRC wants you to go to at least to 5 seconds, but the ground motion models are now very well constrained to
leave them
10.
all the way down there to
Yeah,
10 to 10
they're very
seconds?
well constrained.
Yeah, because at Fukushima, one of the things that added uncertainty about water inventory in the pools, where they couldn't get. I mean, this is why we've got level instrumentation going in. But there was the ground motion at low frequencies occurred for such a long period of time that before the lights went out and they evacuated, there was a GE worker that was in the refueling deck, and he said he observed water sloshing over the handrail out of the pool, which is
A lot of sloshing.
that's.
Well, that motion went on for a very long time.
I know, but so.
In waves.
But I think that the most important fragilities that we're worried about here are being in the 5 hertz, the conclusion that they tend to be bounded just by the difficulty to propagate energy over long distances in this frequency range is a quite important one.
Right. So that's why we're going to see when we say what's the impact of making larger earthquakes. Okay, so that if the faults can produce larger earthquakes, and that's where the science is moving. All of the recent work in California is saying allow for rare occurrences of faults rupturing together and making bigger earthquakes.
I think this points back towards the fact that the most important vulnerabilities are going to come from sort of the wrong combination of things with smaller earthquakes. And And it's the same thing. If you focus only on the really gigantic earthquakes, you're missing the most important source of risk, and you may not be doing the right things.
Yes.
Norm, we've had a concern in the community in the last 5 years about the high-frequency equipment, switches and relays and stuff like that that's sensitive at 15 and 20 hertz. And if you're back in the east, that's got to be just the real close-in stuff. You can't. I mean, the North Anna was right under them, but if you don't get very much further away, it just doesn't get to you.
In the east, different issue. That 10 hertz, 15 hertz stuff propagates a long way in the east.
Is that right?
Yeah, the speeds.
Very high Q, right? So there's much less damping in the crust. The stuff goes for a long ways. Yeah, it's not gone by 50 kilometers at all.
Is that right?
But this would also, but you say that when you take these averages, you're accounting for also somewhat the type of geologic media where the earthquakes are happening,
Absolutely,
right?
sure.
Because, clearly, and even with that, it's clear that when you look at your comparison versus the global average, that...
Could you go to the next slide, because he jumped ahead for me, so there you go. Go ahead.
Okay.
So when we look at this, what is shown here is the 1977 design spectrum that was developed. So it was based on the available global data at the time. Okay. The long-term seismic program in 1991 spectrum was an update of that. But both of these are taking the global models and saying, let's assume they apply to Diablo Canyon. When we then take the local data into account, we get a spectrum now where we see this peak at 2.5 hertz and lower ground motions at the higher frequencies here. But we're going to be getting amplification here. The left-hand side is the power block. The right-hand side is higher because it's a turbine building, which had a lower velocity, so it's going to have greater amplification. Okay? So that's why there's that difference between those. When we look at these, we are still, in this case, bounded by the evaluations we did from the 1977 spectrum. And so our conclusion from this is there's no immediate safety issue from this, and we will go through with the SHAC study to do the rest of the full evaluation of the weights of the logic trees and so forth and alternative models to build up the full probabilistic analysis.
Okay.
And I think is that the last one? Oh, then the other case was, what if the shoreline fault is linked to the Hosgri and ruptures together? So Stu mentioned we actually have modeled this using dynamic rupture models and said, can you build a model where the rupture starts on the shoreline fault and goes to the Hosgri or vice versa? The geometry is such that as the rupture goes from one fault to the other, it's into a releasing bend, which is basically an energy sink, and so it stops the rupture. So all the dynamic ruptures we ran, you couldn't get it more than about 2 kilometers onto the next fault. If the shoreline fault had been on the other side of the Hosgri, it would then be favorable for that, and then the ruptures can go through. So it's just a nature of the mechanics of trying to have strike-slip faulting and having bends and faults. But if we say, fine, but what happens? What if you do that still? So now we put a magnitude 7.3 on the shoreline fault, so the shoreline linking up to the Hosgri and onto the San Simeon fault, you would get a bigger earthquake, and if we compare that here, it's now growing, so it's getting higher. But because of that previous plot I showed you where things don't scale that strongly with magnitude at short distances, it doesn't move things up that much. Okay, so we're really not very sensitive to magnitude, and that's not the thing I worry about. People say, what you asked earlier, what do you worry about? The biggest issues for us are the angles of the faults, the dips of the faults. Those are the things that most impact what the ground motion is going to be in terms of the near fault ground motions.
One more question. In the sort of the 5 hertz range where many of your fragilities are, it looks like you're showing with these curves that actual peak accelerations will be significantly lower than the design
Correct.
basis.
Right.
But I'm curious, it's not just the acceleration, it's also the duration, right? So is there any basis to say that might change?
The duration would be longer, but from these big earthquakes, you would feel it for a long time, but the duration of strong shaking really doesn't go up very much.
Actually, I guess I'm not sure on the fragility of equipment. If you're exciting it at a resonance, it depends on how long you continue to dump energy into it, whether it's going to break, right?
But most of the fragilities are really
Driven by peak acceleration.
yeah, they're not driven by
the number of cycles.
fatigue. So they run them, when they do shake table testing of equipment, they run them over and over for long cycles, but it's not a fatigue.
It's not just
failure.
fatigue, it's amplification. Because if you're in a resonance, then you're adding energy.
Sure.
So your deflections will get larger and larger and larger as you continue to shake at the resonant frequency.
Right, but when you're at these distances, the strong part of the shaking at those large amplitudes lasts for about 10 seconds, even as the earthquake gets bigger, because then after that you're going to have shaking, but at a much lower level, maybe 20% of that level. And then it shifts to lower frequencies
Even if
as
it goes
well.
on for another minute.
Yeah. Yeah. So
Okay.
we see that a good example is the Landers earthquake. So magnitude 7.3 earthquake, you would see very strong shaking, and then it was over in about 5 or 6 seconds, but a low level went on for another 40 seconds. So that's a really common feature of what's going on. But don't think
actually,
of...
I guess, basically, does that, I'm trying to figure out and understand, but since high frequency doesn't propagate very far, that means that it's coming from a short distance, it's not going to last very long. Is that an appropriate interpretation? And then
The
the
way
lower
that-
frequency comes from longer distances? And
correct. So it lasts
the
longer.
duration is longer?
Yes.
And that means that the duration of shaking at higher frequencies is generally going to be shorter? Is
Than
that-
here. So at lower frequencies, it'll be a longer duration. That's correct.
Which is certainly the case with the great Japan earthquake, because there at low frequencies, it went on and on and
Go on for
and
minutes
on.
from those very big
Yeah, but
earthquakes.
it was 70, the distance was 70 kilometers away the closest.
Yeah. Okay.
I think that's the last one. So our summary here, again, that we have potential for making larger magnitudes. Slip rates have generally been a little bit smaller. They only affect our probabilistic results, right? So with a reduced slip rate, my probabilistic hazard goes down because I'm building up less energy. But this has no effect on the deterministic part. It only affects the probabilistic. We have this great increase in the detail of our site velocity information, really an unprecedented view of what's happening that is not available, I think, in any other place in the U.S. in terms of this detail. And then our updated ground motions remain bounded here when we do a deterministic analysis. It's bounded by the 1977 spectrum. Margin, measured as the difference between our current estimate and the design basis, is larger than previously thought. It wasn't intended for those previous spectra to be conservative, but our new information shows that they had more margin than we had estimated.
So one of the things I've been concerned about is that for some weird reason, we spend a lot more time on seismic safety for equipment than we do for people, even though, in my judgment, the people are equally or more important in responding effectively to accidents. So I'm curious, in the fragility analysis, are people also going to check we've got some furniture which is, has weights in the bottom of it, and there's a whole bunch of stuff in the workspace.
Nose in the back, but he's...
I'm not the right person to answer that for you.
This is really good work,
Yeah.
but if you don't use it to also confirm that the people are going to be safe during the earthquake, I think you're missing a big chunk of what you could be doing with this that would also translate off to all sorts of other civil infrastructure where you could save a lot of lives in the long term.
Okay.
Yeah, I'm going to play something back to you that I assume you'll nod, which is that this is, in a sense, this is data, which then is this is data. These are data, which are the feedstock for the SHAC analysis, which is then going to do the probabilistic integration, and then later after the integration, you got to do the differentiation too in the probabilistic SHAC process. Is that right?
That's correct.
Yeah. And that's all got to get done in the next 6 months? Are you going to do that?
Yes.
Huh? I mean, of course, a lot has been going on in the interim, of course.
But the models are yes, the models will be done by this year, so that we'll have our full updated hazard completed by March.
All that source work Any of it modified or upset by any of this?
Modified or upset?
I mean, you notice you had 3 source workshops, and
uh-huh.
you know, and the characterization of the sources.
They are using this information, and so yes, the model is different because they have this information.
I mean, for example, the extra length and that sort of thing, and
they know that, yes.
Extended to the south, and also all of those extra lengths have uncertainty distributions, which capture whatever your state of knowledge is of the range, not just the center, but the range.
Mm-hmm.
So that's all.
That's being all incorporated with alternative interpretations of what's going on.
Now, if I may go back to your summary,
Thank you.
You talk about the magnitudes would be larger on Hosgrid and shoreline, and then the last bullet is the margin would be now bigger. I think you may have touched on that already, but would you please elaborate?
So we need to, in magnitudes, let's use the right, that there's a potential for a larger magnitude. I don't know that they will be larger, but if it's a bigger area, then it can generate a larger earthquake. The margin comes not from the magnitudes, it comes from the ground motion model.
Right.
So there's 2 parts. We have to characterize the source. How big is it? What magnitude? Where is it located? What is its geometry? And then another part is I use the ground motion models to estimate how strong the shaking is.
Has to go from there to you.
The big change that we've had from what was done in 1977 and what was done in the 90s is an improved ground motion model. That's the big change. That's why there's a difference in those spectra, not from the source characterization.
So you have better characterization of the source term, and at the same time you have better modeling of the ground motion.
Correct. And the big change comes from the ground motion side of the
And the extra confidence that you have that you didn't have because of all this, because of the data.
Correct. We have much larger data sets than we had before, and we now have some local data that we can use as well.
To help you to calibrate and correct the global model.
Correct.
Right?
I have a question. 2 comments from members of the public I'm curious to get your response to. One is that Diablo is sitting on faults. And second is someone brought up today the Loma Prieta earthquake, and I was curious how that fits into what you're doing.
Okay. I'm not quite sure what the question is. So how does the Loma Prieta earthquake fit into this?
Yeah, I mean, you have other earthquakes, San Simeon and others you've been looking at.
Loma Prieta was too far away to be recorded here.
Okay.
So that we have to have earthquakes that are strong enough to be felt.
So it just didn't have the impact here because of distance.
Correct.
I think that was more just an observation. Big earthquakes can happen. And
Right.
furthermore, I now am convinced that big earthquakes can happen on the Hosgrid. The return frequency of under 1,000 years, it means that at some point in the future, this is going to happen on that fault. And it certainly, based on this analysis, is active in the sense that
There's no doubt the Hosgrid is active. A couple millimeters a year slip rate is an active fault.
it needs to be considered within the design basis of the plant for sure.
And your first question was
Just a sort of a statement we've heard a couple of times that Diablo is sitting on faults.
yeah. So yes, we are near several faults, and so the issue that you face here is actually, and it sounds counterintuitive, we know better what's happening in close because the models are more stable, and having, so with several faults, if I change the characterization of one fault and make the one fault higher rates and another one lower rates because they have to all balance the tectonic model, it just sort of moves the contributions around. So the way you deal with multiple local faults is you have to have a very rugged, high design basis. So that's what's done. So this area has higher hazard than other nuclear power plants, but it has a much higher design basis than other nuclear power plants, and we're getting a risk number that's lower. And that's really the key, is that it's a combination of hazard and then your capacity to figure out your level of safety. It's not just the hazard, and it's not just the capacity. So those 2 things have to balance together.
I guess the basic question is the plant sitting on faults?
Is it sitting on faults? So The Diablo Cove fault, right? So there are bedrock faults in the foundation. So the fault that they talked about that they could see exists. So there's a fracture. You know, whether that only goes to depths of tens of meters. That doesn't make big earthquakes. Remember, the energy release that we talk about is the area. I need hundreds of square kilometers to start to get enough area. So all of California has bedrock faults. They're all, if you go look, you're going to find them. So yes, there's a bedrock fault there, or a fracture in the top tens of meters, but it's not a seismogenic source. And I think if you even went to the point of saying it's seismogenic, it is just a tiny little thing that's too small to release any energy, to release significant energy.
Okay, I understand. Thank you.
Other questions? So
We are well over.
earlier, Dr. Lamb asked one of our speakers the question, what keeps you up at night? And clearly what we're doing is keeping you up at night, given the hour.
But
So
he's a
thank you.
Californian. It's not as late as you think.
Thank you for your presentation. This is the point in time where we now will move into public comment period.
Let's make it.
And so,
Keep it short.
we will take as much time as is needed for public comment.
But we're going to run the clock.
Okay, all right.
There we go. No, I screwed up.
Okay, this is Dr. Gene Nelson again. I had the good fortune to have a conversation with Dr. Abramson a few weeks back during the open house at the Energy Education Center. And there was a core concept that he talked about to me then that I think should be mentioned to the Commission and to the public who are both present here and who are, distant from us. And that is the concept of aperture, earthquake aperture. And it's a good way to summarize that essentially the impact of an earthquake is going to be that is closest of a given fault is going to be the stuff that's closest to you. It really does attenuate very quickly. And so I just wanted to make sure that concept of earthquake aperture was captured, and maybe you can refine my comments just a little bit more as somebody who regularly lectures on this.
Thank you. Additional comment from the public? Please introduce yourself for the record.
Okay. Good evening, David Weissman, Alliance for Nuclear Responsibility. And I thought of what happened earlier today. There was a brief discussion by the panel where earlier regarding the report on once-through cooling, you had a bit of a discussion as to whether it was going to be called a draft, a preliminary draft, a final preliminary draft. You couldn't quite decide, but eventually settled on it. Might I suggest that what Pacific Gas and Electric is calling a final seismic report also should have been maybe had the same level of discussion. Is it a preliminary draft? Is it a final preliminary draft? And I bring this up because at 6:16 this evening, Dr. Nishenko mentioned that to reduce the range of what they were deciding to cover to create the tornado chart, and they did so with the input of the independent peer review panel. That was at 6:16. It's 8:20 now. That was the last we heard of the independent peer review panel, which kind of mirrors exactly how the process went in real life. The last we, as the public, heard of the independent peer review panel was on July 11th of 2013 at a meeting at which, coincidentally enough, the panel raised a number of questions concerning the topic of discussion tonight again at 7:33 and 7:49 p.m., which was when Dr. Abramson said in response to a question, not enough time to get the data, so I went and got readings from around the world. Then at 7:49 was backed up with need more data, have only had 2 earthquakes. And this was exactly the point that the independent peer review panel raised. And the public never heard from them again. And we're assuming PG&E didn't engage or they weren't engaged. And this is rather a concern because as they were appointed by the Public Utilities Commission and engaged with being the ombudsman for we, the ratepayers, to make sure that the study had a fair and open review. Now, we haven't heard from them. That report was delivered to them the same morning the story broke in the papers. But it's called final. And we suggest that you as well consider that. We went to visit the Public Utilities Commission and were assured that they would take a review that would take 6 to 8 months. That puts us past the SHAC deadline of March. Their first meeting, October 23rd, followed by one on November 17th. As you have attended the SHAC meetings, Dr. Budnitz included, you might want to be a participant in this independent peer review panel, because until then,
We will be.
I don't think, as the member of the public and as a ratepayer who paid for this study, we would put the label final on it, because the ombudsmen who were assigned to look after our interests were not consulted. Where is all this raw data? You may also ask either Mr. Klimchak, who's here, or if Mr. Halpin was here, their statement recently that everything would be made public. But what exactly would be made public? The raw unprocessed data that could be reprocessed and re-examined? To whom would it be made available? And when would it be made available? And those are questions that remain unanswered to this day. Thank you.
Thank you. Additional comments, questions from members of the public? Okay. Not having any, perhaps we should discuss both presentations and comments from the public.
Yeah, I just have I had a comment on the last one, so let me just say it. There's going to be a meeting in 2 weeks of the IPRP, and Per Peterson's going to go, and there's going to be a meeting on November, I can't remember, 18th or whatever, I think 17th, anyway, whatever it is, it's on my count, it is the 17th, and I'm going to go. So we're going to track that process all the way through. I mean, that's our obligation, we're going to do that. So you should be assured that at least we're going to track it, as we have tracked the SHAC workshops as well. And so we're watching that. I just want to say, I don't care what they call the thing. The fact is that until the IPRP has weighed in with its review, it's not going to be final. And I understand that, and I suppose PG&E must understand that. I can't deal with the public. I'm me. What the public understands, there are 30 million Californians, and I can't deal with what they think.
The question was, what does the public understand?
Well, I do appreciate Mr. Wiseman's comment by urging the committee to consider what Dr. Abramson and his colleagues' presentation as preliminary.
Yeah, well,
I think that I am comfortable with that label.
Yeah, I already answered that. I mean, that's what I think it is. Okay, and I don't have any problem with whatever anybody calls it.
Okay. Any responses from PG&E? Please to the microphone, because otherwise the transcript is very hard.
There are people watching streaming and stuff.
All right, so this is Stuart Nishenko
Raise
again
it
from PG&E, and I would just like to respond to Mr. Wiseman's comments about our efforts for transparency. We have made all of the data that we have collected for this project available on 2 public websites. The marine data is with the USGS website, the National Archive of Marine Seismic Data, and the land seismic data is presently with IRIS website, which is a university consortium. So that is part of our commitment to transparency and making this data available for people to look at, to review for themselves what we have seen, our interpretations versus something that they would come up to. With the statement about peer review, there are numerous levels of peer review that have been undertaken in the process of compiling this report. Each individual chapter, while we were writing it, went through what we call an independent technical review process, because this whole report was written under what we call a nuclear quality assurance process. So it was reviewed by an independent reviewer. This committee is reviewing the report. The Nuclear Regulatory Commission is reviewing this report, as is the IPRP. And we will take everyone's comments under consideration when they are made and look at it and evaluate those comments moving forward. Because at the end of the day, this report is a snapshot. PG&E has a long-term commitment to monitor and stay on top of seismic safety issues for Diablo Canyon as part of its long-term seismic program. So what we do today is a snapshot and one increment in terms of a larger decades-long process that we have been doing since the plant was initially licensed and will continue into the future. Thank you.
Thank you.
I have a question for you. And I mean, maybe it's for Norm also, but this data set, I'll call it, I mean, it's a lot more than that, but let's just consider it a data set. This data set and the information derived from it are going to be used by the SHAC Level 3 group to inform their ultimate result, their analysis, right?
Yes.
I mean, we said that to Norma. I know that. I'm just saying it so the public will understand it and you know where I'm going. And there is always not only the possibility, but the probability that there'll be new information which would inform it if you did it next year or the year after. So in that sense, the SHAC result itself is a snapshot in time at that time, right?
Absolutely.
I'm not arguing, just
I think you can think of it as a living process.
Norm and I are involved with something else where the question about how long it's supposed to last has arisen. And I can tell you, it doesn't last any longer than that day, although you hope it has some durability, but you never know because new information comes in or new analyses or a new interpretation by a new expert. So you're not claiming any more than that's what that is. Now, let's suppose that 3 months from now or 9 months from now, either the IPRP group or some other expert somewhere in the world comes up with an insight or a new interpretation or something that would modify what you have now published today. What does that tell you about the SHAC study that's coming out in March? It only tells you, as far as I'm concerned, that the SHAC study coming out in March is based on this, but not on what that would be, because that would be later.
They're not prescient, but they do the best they can with the information they have at hand.
Okay. So I'm not complaining, just trying to understand that it's always a snapshot in time, and it can never be more than that.
But I think there's the best that we can do is to set the ranges and the uncertainty bounds such that when the studies are done in the future, they're within those bounds.
Yeah,
that's a success for us, right?
Yeah, I understand that. In fact, as you know perfectly well from the SHAC guidance, we speak about the center of the body and the range. And if you've captured that, the fact that it might move around inside that, if you have confidence in that range, you still feel as if that's a success.
Correct. Now, when the IPRP comments come back, if a significant revision is made, we revise the studies. We don't simply say we're done and we're not going to look at it again. So that goes on. I think as well the main benefit of us putting this data in the public domain so that people will look at it is to get the university and USGS researchers evaluating that. So we expect they'll be but this will be going on for years.
Or all over the world.
Yeah, people will be working on these kinds of data and seeing what they can pull out of it. No one has had information like this to work with. So new techniques will be developed and so forth. As those come out, we have to incorporate that and say, what does that mean for us? So the hazard analysis isn't done when the SHAC study is done. That will mark the end of one phase and say that's what the position is as of next year. And then we will still go on and be doing incremental updates or checking when changes occur. And likely another major update in another 10 years where everything is looked at again.
I mean, I'm not complaining about any of this, but I just want to play it back to you. Your statement is what I said 3 minutes ago. The SHAC study in March 2015 is going to be that snapshot in time. That's your best state of knowledge at that time. Nothing more, but nothing less.
Right. But the state of knowledge not being here is the answer. Here's
your
the
state of
range
knowledge.
of credible solutions or
Your state of
scientific models. That's correct. Yes.
I mean, the state of knowledge with its whole, the center of the body and range, the sort of thing that we always talked about. Is that right?
Yes.
Well, I certainly fully agree with
Thank you.
what both of you gentlemen is saying to the committee and also about Dr. Butler's comments. But I do think Mr. Wiseman's inquiry is meritorious in the sense that additional to university staff, Mr. Wiseman and his organization is prepared to examine the numerous assumptions involved in this in this approach. I think anybody who has vested interest in examining the assumption will certainly advance the safety agenda.
Yeah, I don't have anything more to add to that than just that it is, by definition, a snapshot at that time.
Additional public comment?
Yeah, Sherry Lewis from Mothers for Peace. Dr. Budnitz, I wonder why you react so strongly against the word final. Mr. Weissman was only saying they call it final.
And I said I didn't care what they called it.
Well,
because it's not final.
Well, right, but if they call it final, then the public is going to think there's something final about it. So it gives a perception that isn't real, and you're agreeing that it's not real.
No, wait. They can call it final if that's what they think. I can say it isn't because that's what I think. No, I don't think that's a small point. It's a big point. All right? It's a big point.
Aren't they mistaken in calling it final?
It doesn't matter what I think. If that's what they think, they can call it what they want.
Well,
but I know that it isn't. Okay?
Yeah, but the point was that it was going to confuse the public.
Well, I don't know what to do about that because we don't have any authority here.
Okay.
You got to remember, we don't have any authority at all. Right? It may be a problem, but if you want to complain about that, you got to complain somewhere else. All right?
I'm sorry, I'll take 10, 15 seconds. Yes, I got an explanation that I will transcribe from Drs. Nishenko and Abramson. But in the transmittal letter that came from Chief Nuclear Officer Ed Halpin to the NRC, in which the report was submitted to the NRC, he says at the end that the underlying data and so forth will be made available to academic institutions and, what was the phrase, something stakeholders after the peer review process. And that's why I'm confused. In his transmittal letter, he appears to give a bit of different information than I just heard here, hence my confusion.
Yeah, I wasn't aware of that because I think I at least knew that it's publicly available.
Well, that's not what the transmittal
which is,
letter
by the way,
NRC.
which is great.
Right, but that's not what the letter to the NRC that we were CC'd on said, so hence the confusion.
Okay.
Yeah, I understand your confusion, and that really is not a small point.
So at this point, absent additional comments, okay.
Not on this subject, but another subject.
Okay, so at this point, I'd like to thank our speakers this evening, in particular for staying as late as everybody has. As I said before, we now know that sometimes what keeps you awake at night is the DCISC.
Wait. I have something to add. There are 6 of us up here, and 3 of us flew in from the East Coast yesterday, and for those people, it's 11:30. All right.
So let me see. At this point, our next action is to adjourn the evening meeting unless we have any additional business to cover. So.
I'll just make this point. On the once-through cooling evaluation, I revised our evaluation, our preliminary evaluation, and have sent it to everyone, marked with a marked-up version, and I asked each person to send it to me and just to me, and not to anybody else. So if you can do that, I don't know if you can do it tonight or not.
I'll certainly do it tonight.
No problem.
But early in the morning, if you would, we can have a second draft. I'll have a second draft out, which we can use perhaps for discussion for approval.
And we'll relieve you from responsibility on coming on the public tour so that you have as much time as you need.
Well, I still might make the tour. It depends what time I get my comments
Even
back.
better. Okay. So with those logistical considerations at this point, it's time for me to adjourn this evening meeting and to note that because tomorrow we're hosting a public tour out to the plant, a meeting will reconvene here, but in the afternoon at 1 p.m.
Wait, I just have one more thing to say. The other PG&E people in this meeting live in this county, but Stu and Norm came down from San Francisco, and so I want to thank them especially because it's further away. Actually, Mark Krause comes from up there too, but of the presenters, they came further and need to be thanked for that.
Okay. Thank you, everyone. I know everyone wants to get some rest or at least some food. So at this point, we are adjourned.